Today we study C21, Galileo, Descartes, Kepler, and Newton. You can download the PDF file of this lecture by visiting kpop.org and you will find the table of contents. Our website provides various subjects and related in physics. X and Y are for the general physics, relative to quantum mechanics. We are working on today the Escape from Scientific Absurdity Series C, and in addition, there are electrodynamics, classical mechanics, and quantum mechanics. Okay, why don't we click this C, Series C? You will find the Escape from Scientific Absurdity C series. This one is a C21. Galileo, Descartes, Kepler, and Newton. After finishing this lecture, I will upload this lecture video file to K-pop YouTube site. You can click this. For example, the C20, if you click this, you will find the PDF file. And if you click this, then Korean lecture. 이번 시간에는 C20. And if you click this, you will find English lecture. Today we study C20 and we begin with the C21. Explain why Galileo Galilei is called father of science. Let's read it through. Galileo is the father of science as well as of physics because he first introduced a systematic quantitative approach. Quantitative approach is very, very important. He performed an experiment and he measured quantitatively. That's a very, very important point. And of the natural physical phenomena. This contrasts with the Aristotelian style natural philosophy. But actually, anyone can make an inference from some observed fact with our bare eyes, based on a verbal and qualitative description of natural phenomena in a combination of hasty generalizations. For example, feather falls down the earth very slowly in comparison with a stone. Uh, they generalized this idea that heavier object falls down faster than the lighter one. Nobody believed now, but for a very, very long time, this wrong idea was believed to be true, and the actual measurement was not supported. It's too unfortunate. Anyway, in short, Galileo separated physics from Aristotle's metaphysics. They are trapped inside the imagination. They are very clever to devise some story that is fun, but not based on the fact. Only Galileo Galilei has started science, so he is not Aristotle, but Galileo Galilei is the father of science, and the beginning of the science is the beginning of physics. Physics is the first science in human history. Galileo collected data such as free fall motion. Yes, he did. Through direct measurements. Direct measurement is very, very important. Galileo first employed mathematics as a proper language describing physics phenomena quantitatively. And mathematics is a logic and language of physics. Mathematics doesn't change the fact. It just carbon copy the fact in a quantitative way. The reason why such a thing happened that cannot be solved by mathematics, but through only through the direct measurement of a physical phenomena. And that was began by Galileo Galilei. Galileo introduced the law of inertia. This is the first physics law ever known, and it is now called as Newton's first law of motion. So Newton copied this law of inertia as the first law of motion. Galileo introduced a reference frame to describe motion. Reference frame, because the measured data for a physical phenomena may differ depending on the reference frame or observer. He was the first person to introduce such a reference frame, and the most important reference frame is called the inertial reference frame, in which the law of inertia is valid. Galileo also not invented but improved the magnification of the telescope by a factor of 20. It used to be factor of 3, but it became about 7 times. As a result, he was able to find planets, the satellites of a planet called Jupiter, which was significant enough to confirm the heliocentric system of Nicolaus Copernicus. Copernicus did not carry out a serious observation, but he analyzed the numerical data generated by old astronomers. So, the observation, according to the observation, he analyzed the data and he found that the reference frame, that the origin from which the measurement can be made, can be shifted not from Earth but from Sun. In that case, the data is greatly simplified. That is the basic idea of a heliocentric system. Anyway, direct observation is of the motion of the planet, and each planet has its own satellite. It's Galileo's triumph. Who developed the concept of relative motion for the first time? This is called actually the Galilean relativity. The introduction of inertial reference frame supports the idea that the extension to the three Newton's laws of motion, and he noticed that there is no way to distinguish two inertial reference frames. For example, you are riding a boat and another boat is floating around, and you notice that the other boat is moving. However, you don't have any right to say you are staying there and the other boat, only that boat is moving. In fact, it is possible the other boat is at rest and you are moving in opposite direction with the same speed. So this kind of thing is concept of relative motion, and that is the fundamental background of the relativity. Now we call it a Galilean relativity. And under Galilean relativity, acceleration and force, that is a very, very fundamental thing that happens in the equation of motion in Newtonian mechanics, is invariant under Galilean transformation that transforms observer from one to another. So this is a translation of a physical observation to another observation that can be made by another person with the same regarding the same identical experiment. And finally, it was generalized by Albert Einstein, and the result is called the special theory of relativity and the general theory of relativity. Okay. What is the equation of motion describing Galileo's law of inertia? That is actually the Newton's first law and the special case of Newton's second law. Inertia, moving with the same velocity. So this is position, this is velocity, and the velocity is a constant. And then if you take the time derivative, you will find the acceleration derivative of constant is just the zero vector. So simplistic equation of motion is called a free object's motion whose acceleration is zero, although the velocity depends on the observer in an inertial reference frame. Number 4, what is the equation of motion describing Galileo's law of fall? Okay, an object, according to Newton's second law, the net force applied to a particle of mass m results in the acceleration with the relation F net equals the mass times acceleration. Newton's gravitational universal gravity states that the force applied to an object near the surface of the Earth is the mass multiplied by the gravitational acceleration that is completely determined by the force g mm r squared er hat. This is a unit radial vector connecting the two particles. So this is a heavy object. If I consider particle of mass small m, then the force is toward the other particle, and the radial direction unit radial vector is written like that. And therefore, we can factor this mass of this particle out, and then is g er hat divided by radius squared. This is nothing but the gravitational acceleration that is almost constant on the surface of the Earth. Okay. Therefore, F net equals mg according to Newton's universal gravitation. And actually, even though Newton didn't know about the difference between the gravitational mass and the inertial mass, Einstein noticed that these two masses are identical to each other. That is the equivalence principle. That is the fundamental idea of Einstein's general relativity. After canceling the mass here, we find the acceleration of an object near the surface of the Earth is identical to the constant value that is the gravitational acceleration. Aristotle didn't notice. What is the equation of motion describing Galileo's pendulum? Actually, that is the rotational version of Newton's second law that torque is the time derivative of orbital angular momentum. In here, we are more interested in the final result. After solving this equation, you will find the equation of motion that shows a theta double dot. What is theta double dot? This is a pendulum of mass m and length L attached to ceiling and with a straight line, vertical straight line. And theta is the angle between the pendulum and the vertical straight line. That's it. G is the gravitational acceleration, L is the length. This equation resembles this. What's that? This is F equals ma with the force replaced with minus kx. What's that? That is the restoring force called Hooke's law. The spring mass system tends to return to the point at which the equilibrium happens. Okay, so this is called, if we rearrange this equation, you will find this. We call this mass spring system to be a simple harmonic oscillator. Although there is a sine theta, what Galileo found that is, regardless of this amplitude, the maximum angle for the pendulum to reach from the vertical line, independently of this amplitude, Galileo found that the period of this oscillation depends only on the length in such a manner, square root of length. Okay, so as a special case, we can expand this sine theta as a power series expansion, such a manner, but actually this angle is not large enough. Therefore, we can almost always can simplify this one without making big mistake. We can approximate with this. In that case, it is identical to, mathematically identical to physically different situation, but mathematical structure is a very simple, that is equivalent to the simple harmonic oscillator, whose period is independent of amplitude. Okay. Later, Christian Huygens found the period is exactly expressed as this for the spring and the pendulum. And the more exact formula is found using, if you understand the elliptic integral, what to us it's this expression is accurate enough. And because of his theoretical understanding and physical realization of the clock, pendulum clock, Huygens invented the pendulum clock, and it is still using more than almost 300 years. We investigate the work of Johannes Kepler. Okay, he is very famous for introducing three laws of planetary motion that realizes the idea of Copernicus, the heliocentric model. In fact, all of the measurement was carried out by Tycho Brahe, and he was very good at observation without telescope. He didn't have any telescope. Only the Galileo was working with telescope. Anyway, his data, he has a big data at that time. 777 fixed star observation. He has complete at the time. He was the best observer in the world. And young Johannes Kepler was hired as assistant of Tycho Brahe. And then, even though he was a good observer, he was not able to analyze what the reality is. And Kepler was able to analyze the data. From the result, Kepler showed that orbit of a planet is an ellipse. Area velocity is constant. So, for example, the first law states that sun is at a focus of an ellipse and Earth is surrounding the Earth, the sun, and this is a focus at the sun. If it moves around, if it is very far away, its angle is small, but if it reaches the nearest point, swiping angle is a much greater for the same delta t. So this is called to make these two areas the same. So it is called the area velocity conservation. Later, Newton found that that is the consequence of the orbital angular momentum conservation. And then there is a power law that relates the period and magnitude of the semi-major axis. This is a major axis, and half of this, the longest axis, is called this major axis. This half of this is called the semi-major axis. Okay. So that the third law is called the harmonic law. We shall find later that harmonic law is closely related to the solution of the simple harmonic oscillator. Okay. Descartes. You are familiar with Descartes in the philosophy, in the modern philosophy. However, in physics wise, we are more interested in Descartes in view of the introduction of a Cartesian coordinate system. Cartesian is the adjective of René Descartes. He introduced rectangular coordinate system XYZ, and by introducing this perpendicular three axes representing a point to represent a point in the three-dimensional Euclidean space, it was very, very useful to analyze a geometry in terms of algebra. So great development of a vector algebra was possible due to the introduction of a Cartesian coordinate system. And complicated analysis based on the Euclidean geometry is now replaced with a very simple algebraic approach. So analytic geometry was born by this Descartes. Is there any physics law named after Descartes? Unfortunately not. He derived the Snell's law, angle of refraction. However, although the answer was right, his derivation was based on a wrong assumption that speed of light is infinite. Sir Isaac Newton published Principia. What is the meaning of this book in human history? Okay, he introduced the three laws of motion and Newton's universal gravitation that was combined to explain three Kepler's laws. Newton constructed equation of motion for a planetary motion based on the fact that the force between the sun and a planet relies on inverse square law, and it is attractive, proportional to a constant, and it is proportional to the product of the two masses. Negative sign means attractive force, and here the unit vector from the sun, unit vector parallel to the straight line connecting from the sun to the planet. Okay, this is the Newton's law of gravity, the universal gravity. Using this and his Newton's second law, he derived the fact that orbit of a planet is an ellipse. Depending on the energy of a planet, we can even consider the case parabola or hyperbola. That depends on the energy and orbital angular momentum of the two-body system. Explain what Newton's second law is. F equals ma can be replaced with the time derivative of linear momentum, and where linear momentum is a mass multiplied by the velocity. In Newtonian mechanics, although it is not true in Einstein's relativity, mass is invariant. Therefore, time derivative of linear momentum is mass times acceleration. From this, we divide both sides by the mass of the particle to find the acceleration in this form. So, once you know the force applied to a particle of mass m, you divide the force by mass to find out the acceleration. And after solving this equation of motion that is the second order linear differential equation, and sometimes nonlinear depending on the force, you can solve the track of a trajectory of a particle as long as you know the force. Can explain what Newton's third law is. Newton's third law is if two bodies interact with each other, the force applied by particle 1 and 2, so 2 applies force to 1 and 1 applies force to 2. They are vectors, but their sum is a zero vector. So they are additive, mutually additive inverse. That means magnitude is the same, the common magnitude, but directions are opposite. Additional fact we can derive from this equation is that if we replace 2 by 1, then we have 1 to 1, 1 to 1. What's that? 2 times 1 to 1. 2 times the force applied by 1 by 1. What's that? This is self-interaction, from which we can determine self-interaction vanishes. It is impossible for an object to accelerate itself. Only the external force can produce an acceleration of a particle. Very interesting. Okay, that's it for today. Thank you for listening.